Hello. I'm back for a walk, so I'm kind of scummy, but it's all right. And my dog might whine in the background too, but we'll live with whatever happens. All right, so a magic square is when every row, column, diagonal all adds up to the same number. This one is going to be 15. Now, you could just guess and test, and if you were in class, I would have you do that for a while. I'm going to write the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And just to speed these along, it kind of makes sense that kind of the average would be in the middle. I don't know if that is logical to you. So I'm going to put a 5 there. And then when that happens, do you see how the ends make the 10 here to get to 15? So if I put my 5 in the middle, then I can kind of arrange these around. Now, how these go, I'll have to figure out. So if I do 1 and 9, I don't know, I'll try maybe 8, but see how that's going to be too big. With a 9, I'm already over 17, so it's like, oh, probably not. So maybe try 8 and 2 going this way to get my 15. What else do I have? 3 and 7, right? What am I at? 9, 10, 11. So this guy needs a 4, so 4 and 6. Okay, but then I'm at 6, 7. Ooh, that's good. 15. Okay, so what's left? What have I not done? Is it 3 and 7? All right, so let's see, this is 9. This is already at 15 though, so that's kind of a problem. All right, so then it's like, ooh, maybe, maybe I shouldn't do that. All right, so let's try again. Let's see, maybe let's try what? This is maybe let's see, that's my, okay, let's maybe try 1 and 9 here. All right, and then see what happens. That's 15, that's 15. Okay, so what's left? 3 and 7. So maybe, but I can't put a 7 there. Maybe we'd put a 7 here, and that would be 3. Okay, so now I'm at 8. So I need, yeah, I would need another 7, so that's not going to work. All right. So we can just keep trying to plug away. Even knowing 5 goes in the middle, it's like, oh my gosh, what am I doing here? All right, so play with that a little bit. I'm going to pause and I will be right back. Okay, I just kind of played with it a few minutes more, and it looks like if I do 15, 15, 15, 15, then I get 15, 15, 15. So I think I got it. And you might have a rotation of that, but again, playing around with it, knowing that if you take 15 divided by 3, the average would be 555. So knowing 5 goes in the middle is key, and so forth. All right, so let's look for a pattern here. Some people look at the gaps here. So what are you adding? Adding 9. Some people are like, ooh, I'm adding 11. Let's see, then what am I adding? 25, 36. So here I'm adding, is that 9 again? So then some people are like, oh, maybe I add 11 again. So is that 56? And maybe add 9, which is at 65. And maybe add 11. Hopefully I can do math today. 76, I think. Okay. So some people might look at that. What other pattern might it be? This is 4 times 4. I don't know, 5 times 5 and 6 times 6, but then 4 times 45 kind of messes that up, right? It's not 7 times 7. So yeah, so right now I'm like looking at adding 9, adding 11, adding 9, adding 11, adding 9, adding 11. And again, when you figure out a pattern, it is inductive. You're taking all the information in and you're trying to figure out a rule or pattern. All right. You pay $4.60. This is a price including tax for a sweater. What was the price of the sweater without tax? Okay. One thing with percents that's really good to know is that if you go forward with a percent, you always multiply. So like if you want to find, 6% tax on a $22 item, you would multiply. Okay. If you want, so if you know the percent, like this is 6% and you're going forwards, like it costs $22, what is the tax going to be on that? If you're going backwards with percents, or if someone asks you for a percent, you always divide. So if you get 42 on a test out of 50, you would divide and multiply by 100. That would be 84%. So to get a percent, you always divide. To use a percent, you always multiply. Now this one is kind of weird because you're kind of in a sense going backwards. So let's think about it as if we were going forwards and you would multiply. So you would take the price of the sweater, and an easier way of doing this is do 106%, because what that does is it gives you the price of the sweater all of it, right? That's 100%. Plus, it gives you the tax part of it, which is the other, what is that, 6%? So you're really paying 106% if you do the math forward. And that gives you the price with tax. So if I knew the number, right, the price of the sweater, I could take it times 106%, which would be for the sweater and tax, and I could get that. So going forward, I would multiply. But technically, I'm going backwards because I'm trying to solve for the price. So to undo this, I would divide by 1.06. And so the price is, what is it, $46.50? Kind of an expensive sweater here. Oopsie. Okay, so that would be what, $43.87 with rounding. If you try to multiply by 6% and subtract, it doesn't quite give you the right answer because it's not, you're not undoing the math that you did forward. Going forward, you want to multiply to get the price, and the price that you or the percent you multiply by is really 106% together. All right, let's look at the next page. This didn't print very well, but if you look at the copy I gave you, there's a pie chart, and heating and cooling is about half of what people spend. So suppose that your family spends this on energy expenses. About estimate how much did your family spend on heating and cooling. Okay, so this is all your energy expenses, and really you spend about half, and this is an estimate. So if it were me, I would take half of about what, $2,000, something that I could do in my head. I always think of estimates as something I can do mentally. Some of you might be like, well, you know, Julie, I can take half of 2,200 in my head, so I'd say about 1,100. Totally fine. As long as you can do it in your head, it's a pretty good estimate. Okay. Now, exactly, again, what did I say earlier? To use a percent, you always multiply. So I'm going forward. I know the percent, and I know the money amount that I want to take the percent of. So you would multiply, and again, move the decimal 2 jumps. So I would take 48% of means I'm going to multiply, and I'm doing the math forward. So I would multiply. So then I get exactly, and that would round to about what, $39? Okay. All right, let's look at this one. Suppose a person is dieting, losing weight at a constant rate. 3 months, they weigh 240. After 8 months of dieting, they weigh 200. Okay, so to write an equation, you kind of need to know 2 things. If you think of algebra, y equals mx plus b, this is your rate of gaining or losing, and this is your starting amount or your y-intercept. All right, so let's see what happens here. This person's losing 40 pounds in what? A 5-month time period. So their rate, which is called slope in math, is a negative 40 divided by 5. That is a negative 8. All right, so they are losing 8 pounds per month. Okay, now I got to figure out their starting weight. I could do algebra if you remember it. Y equals mx plus b. I know the input, I know the output, I know the rate. So at the 3-month mark, that's my input. I know they lost 8 pounds per month, and their output was 240. So 240 equals 24. So basically, in that 3-month time period, they lost 24 pounds. So if you go back in time, they would gain that weight. So is that 264? Is their starting amount. If your algebra is like, oh, Julie, you lost me here. It's been a long time since I've done algebra. You can always make an input-output chart. So we have 0 month, 1, 2, 3, 4, 5, 6, 7. We could keep going. We know at the 3-month mark, they weighed 240. And we know they're losing, what, 8 pounds a month. So you could keep subtracting like 232, and you could subtract. But if you go back in time, they would be gaining weight. So 248, 256, keep adding 8, that would be 264. And real life starts at 0, right? Times 0. Like blast off is at 0. This would be a year or a month after dieting. Okay, so this is my formula. Now, we can also figure out what will he or she weigh after. So they started weight was 264. What will they weigh in a year? If I have a formula, I could just type in 12 months into that. So I could use my negative key, negative 8. Make sure you use a negative key, times 12. And their starting weight was plus 264. So they would be 168. Okay, assuming, you know, they can keep that constant. All right, next one. And again, sorry, my printer, and I've tried to fix it, but it's not working. Okay, there's some of these, and I made a video about this online, this type, but you want to let this be year 0, whatever it is. You don't want the calendar year to be your thing, I guess. And this one goes to 2016. So this is year 16. The other cool thing about these is you can call this your starting amount because that's when you're starting your graph. Okay, so write a model that includes estimate for tuition. Okay, so tuition. So my starting amount is 3349. I just need to figure out the rate it's changing by. All right, so it looks like if I copy this right, that it went from 3,349 all the way up to 9,410. So I'm just going to subtract those. 9,410 minus 3,349. All right, so it looked like tuition went up $6,061. And again, don't necessarily use these, but go from here in 16 years. It's going to be the same, but it will screw up your formula if you use like those when you figure out this guy won't make sense anymore. So you need it to be year 0 for the start. Otherwise, you get your start would be at year 0, like between BC and AD, that kind of thing, or before Common Era and whatever the other one is now. I can't remember. But yeah, you don't want year 0 to be the difference between the times. You want it to be the year 2000. All right, so now to find slope, which is your rate, you figure out how much money it went up over how much time. So I'm going to take that 661 or 66,061 divided by 16 years. And so that's how much money it went up. And again, I'm going to be pretty precise here. I might even go past my decimal point. I might write it all because then it's not rounded. All right. So it went up about $378.81 and then some change per, whatever. So then if I wanted to year like, oh, we're in the year, 2023, you could sub in, let's see, from if the year 2000 is 0, that's 23 years later. So we would have to multiply. Order of operations, you multiply before you add. So most calculators will do that, but just kind of remember please excuse my dear Aunt Sally. All right, I'm going to multiply first and then add in that 3,349. All right, so it looks like 12,061 and some change. And I would wait till the very end to round on my math lab. I would use the precise thing. All right, now this last one, again, did not copy well, and I'm trying to fix my printer at home. But this is looking at life expectancy, okay? And in this graph, they're just looking at females and males, so that's kind of what we'll look at. And I think there might be one similar to this on your homework. So if we focus on males here, all right, so right there. All right, so first of all, oh, shoot, I didn't write the years. I'm going to pause and look at the years. They did not copy well. Give me a sec. Okay, same idea. If we're focusing just on men, it went from 72.1 minus 65.6, and that's 6.5. And that's years of life, okay? Divided by how many calendar years? Well, from that to that is 70 years of time? So this is calendar, this is of life. So it's kind of measuring different years here. So I'm going to divide by 70. All right, and I'm going to have 0.092857143 x, okay? Plus my starting amount is that they would live to be 65.6. So again, if I want to figure out in the year, 2030, assuming things keep trending the way they are, from 50 to that is an 80-year gap? 80. So I'm going to take that times 80 years and add in that, 65.6? So it looks like they would live to 73. It's not super old, actually. I thought it'd be older. And again, given this chart, we only have male and female data here. So we would look at the female life expectancies, little better. Okay, so the change in life was 10.8 years of life. Again, still over 70 calendar years, so divide by 70. So the rate is higher for them. 1.5, what is that? 428.